Today we are going to discuss another topic in digital image processing, that is image compression. It is one of the most important topic in the field of digital image processing. So upon completion of this unit or chapter, students should be able to measure the amount of information in a digital image, understand the main sources of data redundancy in digital images, know the difference between the lossy and error-free compression. That error-free compression is also known as lossless compression, and the amount of compression that is possible with each. So the goal of image compression is to reduce the amount of data required to represent a digital image. So techniques for reducing the storage required to save an image or the bandwidth required to transmit it. For example, this one is an original image. When we compressed it, we can directly store this compressed image and then we can retrieve it through some algorithm that will decompress it. And if there is some loss of information, that is a lossy compression, then we are not going to get an original image, that is f of x comma y. So if we compress the image, that will also save the storage capacity. And if you want to directly transmit it through some channel, so that will also store or reduce the bandwidth requirement. So image compression addresses the problem of reducing the amount of data required to represent a digital image with no significant loss of information. So image is a combination of information plus redundant data. Image compression technique falls in two categories. One is a lossless, another one is a lossy. So in lossless, information preserves, so low compression ratio. While in case of lossy, information is not preserved, so high compression ratio can be achieved. So what is data compression? Data compression refers to the process of reducing the amount of data required to represent a given quantity of information. Sometimes we are representing information to a larger number of bits. That is not required. Even a small number of bits can do that job. So because various amount of data can be used to represent the same amount of information, representation that contain irrelevant or repeated information are said to be contain redundant data. So data, there is a difference between the data and information. So data and information are not the same thing. Data is the means by which information is conveyed. So data compression aims to reduce the amount of data required to represent a given quantity of information while preserving as much information as possible. The same amount of information can be represented by various amount of data. So you can see in this example, in example 1, there your brother Ashish will meet you at Santa Cruz airport in Mumbai at 5 minutes past 6 p.m. tomorrow night. So you can send this message, but this message needs a larger memory storage capacity as compared to the next one. So your brother, it means you do not need a name of Ashish. So your brother will meet you at Santa Cruz airport. So we remove this Mumbai at 5 minutes past 6 p.m. tomorrow night. So that has the same information which you are conveying in example number 1. There is another way to represent this the same information. So Ashish will meet you at Santa Cruz at 6 p.m. tomorrow night. So that have more or less same information. So it needs a less memory as compared to the previous two. So now we have to find out what is data redundancy. It contains data or words that either provide no relevant information or simply restate that which is already known. The relative data redundancy RD of the first data set is defined as RD is equal to 1 minus 1 by CR. So RD is a relative data redundancy and CR is the compression ratio. For example, data set 1 or image 1, it carries n1 number of bits. While when we compress this data set, it carries n2 number of bits. So compression ratio is n1 by n2. Now n1 and n2 denoting the information carrying units in the two data sets that represents the same information or image. If compression ratio, for example, in the first image, the number of bits required is 10, and in the second image or the compressed image, the number of bits required to represent approximately same information is 1. Then CR is 10 and RD is 0.9. It means that 90% of the data in the image 1 or data set 1 is redundant. If n1 and n2 are equal, then compression ratio is 1 and redundancy is 0, or relative data redundancy is 0, indicating that the first representation of the information contains no redundant data. But when n2 is much less than n1, then compression ratio will be a larger. For example, once it becomes an infinite, very large value means infinite, then RD tending towards 1. Larger values of C indicate better compression. So types of data redundancy. So there are various kind of data redundancy that occurs in an image. First one is a coding redundancy. Next one is a interpixel redundancy. And third one is psychovisual redundancy. So compression attempts to reduce one or more of these redundancy types. So in this lecture, we are going to discuss about coding redundancy. And in next videos, we are going to discuss about the interpixel and psychovisual redundancy. So first we have to understand what is code. A list of symbols, letters, numbers, bits, etc. are known as code. And code word, a sequence of symbols used to represent a piece of information or any event is known as code word. For example, this G represents the code and the gray represent a code word. And code word length is number of symbols in each code word. For example, in the case of gray, the code word length is 4. So here we have given an example. These are the decimal numbers and corresponding binary number. So 0 and 1s are symbols, so they are code. And the length is 3 and 00 is a code word. Now to understand this one, the gray level histogram of image can be used in construction of codes to reduce the data used to represent it. Given the normalized histogram of a gray level image R, P of R, Rk is equal to Nk by N. So the number of bits required to represent a gray level depends upon its probability of occurrence. So here Rk is the discrete random variable defined in interval of 0 and 1. Prk is the probability of occurrence of Rk and L is the number of gray levels. Nk is the number of times that gray level appears and is the total number of pixels in an image. We had already discussed this formula in a histogram. So that is the same. Now, average number of bits required to represent each pixel is given by L average is equal to summation L Rk PR of Rk, where k varies from 0 to L minus 1. And L of Rk is the number of bits to use to represent each value of Rk. So I am going to explain this with the help of an example. So initially we have a n cross m image and Rk is the kth gray level. Prk is the probability of Rk and Lk is the number of bits for Rk. So average number of bits we have already discussed, that L of Rk into Prk, then summation varies from k equal to 0 to L minus 1. So total number of bits is n into M into L average. So for example, this RK, we have taken a 3 bits to represent an image. So RK, as we have already discussed, that RK is in the range of 0 to 1. It means it is a normalized value. So occurrence of R0 is 0 divided by 7, R1 is 1 by 7, R2 is equal to 2 by 7, R3 is 3 by 7. These are the gray levels for a 3 bit, and R7 is 7 by 7, which is 1. And the probability of this one R0 to be appear in the image is 0.19. For R1 it is 0.25, for R2 is 0.21, for R3 is 0.16, R4 0.08, R5 0.06, and R6 is 0.03, and R7 is 0.02. Now if we go for a code word 1, then it can be 0 will be represented by 000, similarly 1001, then 2010. So we represent it into binary. So we need 3 bits for each number representation. So L is total number of bits, total number of gray levels is 8. So L of RK is 3 number of bits. So L average comes out to be 3 bits. So total number of bits is 3 cross N cross M. Now in case 2, we are using a variable length coding. So different number of bits for different gray levels. So this one is example of case 1 where we are using a constant length coding, while in this case if we are using a variable length of coding, for the first 3 gray levels we are using a 2 bits. So code word length is 2 bits for the first 3 gray levels. For the next bit I am using a 3 as a code word length. For next bit 4 bits, next bit 5 bits, and the last 2 by 6 bits. So the average length is 2.7 bits. The compression ratio comes out to be 1.11, that is about 10%. And RD is equal to 0.099. So 10% of the data set are redundant. So assigning fewer bits to the more probable gray levels than to the less probable ones achieves a data compression. This process is commonly known as variable length coding. So later on I am going to explain you that how we are going to construct this variable length of coding. In the next lecture we are going to discuss about interpixel redundancy.